Now, in the previous videos, we've seen moving average models and autoregressive models. The more general class of ARMA models then combines both in one model equation. So a stochastic process follows an ARMA of order P and Q if it satisfies this model equation on the slides, where we have P lagged values of Y included in the model and Q lagged error terms. So the first index in parentheses indicates how many AR terms are added in the model. The second term indicates how many moving average terms are included in the model. Equivalently, in lag operator notation, we can write the model like this, where all the AR terms are collected at the left-hand side and all the moving average terms are collected at the right-hand side. In a similar way as before, the stability of the process can be verified. Now, how do the parallelogram and partial parallelogram of an ARMA model look like? You can see here an example of the most simple ARMA model, so an ARMA 1-1. Based on the parallelogram, you would probably have to specify a moving average of order 7 based on the significance of all these autocorrelations up until lag 7. Based on the partial parallelogram, you might think of trying an AR4. Now, neither of those are actually parsimonious, since quite a lot of parameters need to be estimated. 7 for an NA or 4 for an AR. In such a case, ARMA models provide a nice way out to still parsimoniously capture such more complex DGPs. Importantly, this of course does not mean that you would be specifying an ARMA 4.7. Not at all, since that model would contain even more parameters, namely 13. But if you see such a parallelogram and partial parallelogram that don't look nice in the sense that they implode after a low order lag, just try out a simple ARMA model. First an ARMA 1-1, then move on to an ARMA 1-2 or 2-1 in case the residuals would not look like white noise yet. I've summarized the roadmap over here on this slide that you would typically follow for a univariate time series analysis. Always start by plotting your time series. Then probably you will see that you need to transform it in order to get a stationary time series. And we will rely on so-called unit root tests to inform us whether a time series is stationary or not. These are all things we will discuss later on in this course. For now, let us say that you have a stationary time series. And so you can continue by making the parallelogram and partial parallelogram, since these are useful tools to specify an appropriate time series model. The parallelogram can be used to specify an appropriate moving average model, the partial parallelogram to specify an AR model. And when neither look nice in the sense that they implode after a low lag order, then you can resort to ARMA models. After you have specified the model, of course, you want to estimate the parameters, which we will do via maximum likelihood. And then finally, once you've obtained your estimated model, you want to validate it. Namely, you want to check if the residuals are white noise or reasonably close. Now, I will conclude our first lecture week here by discussing the estimation procedure that we will use to estimate our time series models, which is maximum likelihood. In general, maximum likelihood estimation finds that parameter value that maximizes the likelihood function given the observations. Or intuitively, it looks for that value of the parameters that makes our data most probable. As you might know from an earlier course, in order to compute the maximum likelihood estimator, you need to specify a distribution for the error terms. In this class, we will consider Gaussian maximum likelihood. And the parameters that need to be estimated in our various models will be conveniently collected into a single parameter vector theta. What the parameter vector precisely is, of course, depends on the model that you want to estimate. And I've summarized them over here for ARMA models. Now, how does maximum likelihood work for stationary time series model? Well, let's have a look at the example of an AR1 case. We need to start from the joint density. And here in this formula, I will make use of this formula at the bottom over here, which re-expresses your joint density of two random variables as the product of the conditional density and the marginal density. So we can rewrite this full joint density as the conditional density of yt, conditional on all other terms, times then the joint density of all the other random variables. Now, by continuing this recursive substitution trick, now expressing this joint density as the conditional one of yt minus 1 conditional on all the others and the joint one of all the others and so on, you arrive at this expression where we end up with the product of conditional likelihoods times the marginal density of the initial observation, which is y1 in this case. And from here onwards, there are two possible ways to continue. Either we could specify the distribution of these initial observations, but this quickly becomes cumbersome, as you will see in Hamilton. So in this course, we will take another route and work with the likelihood conditional on these initial observations. And then we only need to consider the first conditional likelihood part over here. Now, what these initial conditions are, of course, depends on the different models, as I've summarized here on this slide. But the remainder of the derivations involve two crucial steps. First, you need to compute the conditional log likelihood, where you start from the log of the joint distribution, conditional on the initial values, and you perform this recursive substitution trick to get to a form which has the product of all the conditional densities. Once you have this expression, where I deliberately left the dots in place since the details depend on the specific model that is being used, but so once you have this expression, you need to continue to find the parameter that maximizes this conditional log likelihood. Have a closer look in Hamilton how these steps can be done, and you will learn to perform these steps in your tutorial assignments. So here we will have a closer look at Gaussian maximum likelihood for AR and MAQ processes. Now, this brings me to the end of the first lecture. After this lecture, you will be able to read to the necessary parts of Hamilton chapters 2, 3, and 5. And you also have all the details to prepare for the first tutorial assignment. Good luck with your preparation.